Like I was saying, today's pictures is from this book by Akopian, really nice book. Geometry in Figures. There's only pictures and you're supposed to come up with the statement and the proof of the pictures. All right, so I guess we can just begin. We might as well just begin. We'll start with some simple configurations, and then from there we can see if we can go to more advanced configurations. Okay, so the first one, can someone write the statement? What is this about? Yes, we have a right triangle, a median, yes. What is the picture trying to communicate to us? So you guys see those marks? Those marks suggest that we have those two segments which are congruent on that hypotenuse. And the dashed line is the line where you need to draw a conclusion. Yeah, so apparently the claim is that the median on this right triangle, the median drawn to the midpoint of the hypotenuse, measures half of the length of the hypotenuse. Yes, you guys are right. Some people are suggesting that I can also draw a circle, that this would be a circle, and boom. That's pretty much the center of the circle, and we are done. Right. Alternatively, which I think it's, how else can I prove this statement? 30, 60, 90 triangle would be a special triangle. This works for any triangle. Whatever the angle here, 25 degrees, 65, this statement is still true. Okay, some people are suggesting some angle chase. Yeah, so we can try some angle chase. For instance, do you guys want to label the vertices? I mean, well, one thing is, because the statement of the problem is on this picture, I might as well just draw a new picture, because it will be distracting me, right? So this symbol over there. Let me just go ahead and draw a new picture. So we have this right triangle. There's a right angle here. Let me go ahead and draw the median. So right now, the only, well, this doesn't look like a median. Oh gosh, okay, there we go. Okay, this is more like it. All right, so this is a median in this, on this right triangle. So these two segments, they are congruent. We need to show that the median also is congruent to each of these pieces. All right, yeah, so angle chasing. So if you do a naive angle chasing, if I label this one as alpha, this angle over here will measure what? Yeah, that one would be 90 minus alpha, right? And if I label this one as beta, this one will be 90 minus beta, because the whole thing was a 90-degree angle here. And so this angle is, this angle ends up being, because it's the external angle, yeah, so it turns out to be alpha plus beta. I mean, yeah, but then we are kind of stuck. So the expectation was that, for instance, one idea is to establish this is an isosceles triangle. If I want, because I want to show, if you label them A, B, C, and M, I want to show AM is equal to MC. So basically, all I want is to show that these two are equal in measurements, right? But then there's a concern here. What is the concern? What am I missing here? What is it that I have not used during this angle chase? When I first calculated this, I made use of the fact that this is a 90-degree angle. And then when I calculated this, when I calculated this again, I used the fact that this is a 90-degree angle. But yeah, we never made use of the fact that AM is a special Chavian. It is a median here. All I did was I just used M as if it's just any point on BC, and so that's the part which is missing, right? So we need to somehow also, during my angle chase, or before or after, I want to make sure I involve the fact that M is the midpoint. All right, so another attempt. Here, let's draw. Well, we are running out of space as well, so we might as well by now finish the proof. A, B, C. Okay, so we have again this right triangle, the median, there we go. This is the midpoint M. Now this time I will try to be a little bit more careful. Mass points, maybe. I don't know how to do it with mass points. All right. Okay, wow. So we have Brian here in the room who provided a detailed sketch of the proof. Thank you, Brian. So he suggests that we should drop a perpendicular to AB. Let's go ahead and follow his lead. What happens if I drop a perpendicular? So let me label this new point as N. Oh, sorry. He meant to AC. Okay, let's do it to AC, I guess. Let's drop a perpendicular to AC. Sorry for that. Okay, so so what do we know about MN? Is there anything? Ah, nice. MN is a special line now. Yes, good. Do you guys see the relation between MN and AB? MN and AB, they are parallel to each other. Why would they be parallel to each other? Yeah, so because of the way I constructed N, right? This is a construction. So I draw MN in a way that such that this is a 90-degree angle. A and M is a 90-degree angle. But this angle is also a 90-degree angle. So we have this reference line AC, and we drop two perpendicular to AC, namely AB and MN. So those two lines better be parallel to each other. But now we're in for business. There's quite a few angle chasing that I can do. For instance, this angle ABC is congruent to which angle? Yes, that would be NMC. That's correct. And well, secondly, this angle over here, how about this angle? Angle BAM is congruent to which angle based on the fact that we have two parallel lines? Yes, that would be congruent to this angle over here. But now let's think further. We have, I think some of you guys already suggested that triangle ABC is similar to another triangle. Can you tell me which one? Triangle ABC is similar to triangle because of those parallel lines. ABC and MC, yes. NMC, yeah, that's correct. So those two triangles, them being similar, suggests something. I don't know if the exact name of this theorem, but obviously I can look at the length ratios, but one thing is clear. Actually, I didn't even need to use this. Well, it comes directly from this similarity because we have these two lines which are parallel. And on one side, we have equal segments. On the other side, we should also have equal segments. Have you seen this before? I think sometimes they call this the splitter theorem or something like that. Huh? So, but then we are done. Why are we done in our proof? Because if you focus your attention on triangle AMC now, triangle AMC, we have MN, which is an altitude in that triangle, which splits the base into two equal segments. So that would suggest that these two angles, they are technically equal to each other. Yeah, this is a special feature of isosceles triangles, right? This is an isosceles triangle. AMC is an isosceles triangle. Why? Because the altitude splits the base into two equal portions. And so these two angles, because it's an isosceles triangle, these two segments are necessarily equal. In fact, even these two angles are equal and so on. So therefore, because those angles are equal, it means these two angles are equal. Well, basically the same thing. So this thing is also equal to that because earlier we suggested that it breaks this into two equal pieces. I think I kind of, this proof is nice because we had to come out of our comfort zone and think about the idea of drawing this additional line. This was a game changer, drawing this perpendicular. And we could have as well draw a perpendicular to here, that we could have solved the problem in a similar way as well. Can we do mass points? Probably yes, but yeah, I don't know how to do it with mass points. All right, so when we come back, I think another solution which kind of was nice is recognizing that because of that 90-degree angle, we have this circle here. All right, and well, this 90-degree angle subtends the diameter. So this is the diameter. The midpoint of the diameter is the center of this circle. And wait, you guys can't hear me? Test. Okay. And as a result, yes, these are both radii, r, but because this point is on the circle, this must also be a radius, right? So it's a pretty good deal. All right, let's go directly to the second result. How about this one? What is the statement trying to communicate to us? Oh yeah, so check your speaker adjustments. If you can't hear me, I think yes. Oops, let me double check. Yeah, I think I'm not muted, so yeah, you guys should be able to hear me. Okay, yes, so we see that we have 4 points on the circle, A, B, C, D. Then if 4 points are concyclic, A, B, C, D is a cyclic quadrilateral, as we call it, cyclic, then necessarily that means then, if this statement, then those two angles better be congruent. So angle A, well, when I say A, I mean really DAC, better be equal to angle DBC. Now we need to, the way you guys are familiar with it is because they subtend the same arc, those two angles which are on the circle, they better be equal to each other. Can we use Pascal to prove it? No, I wouldn't use it. Yes, CAD and CBD, they intercept the same arc. As a result, they must be equal angles. To be honest, I don't even remember how to prove this. I think it had to do with, oh, okay. So there's a couple of interesting ideas already where to start with. Okay, so some people suggesting that I should first of all label the center of this circle. Let's do it. So this is the center. Then what do I do? Yes, so then we can start joining some lengths. Okay, so yeah, let's join the chords. Okay, we have a chord here. And yes, so let's go ahead and construct some radii. So for instance, if I construct this radius, and this one, okay, so let's focus on the first one. Let's try to understand it. It splits here alpha, beta. Let's see if this does it. Okay, if this is alpha and beta, I think necessarily because we have an isosceles triangle here, this one is also beta. And then this whole angle, that's alpha. So if I were to extend it, I guess, if I were to extend this segment here, AO, then necessarily this one is an external angle on our triangle. Well, this is something that we didn't prove, right? But we might as well just prove it. This external angle is just alpha plus beta, right? Alpha. One way to prove it is just to draw a parallel line to this. And because corresponding angles, this is alpha, this is alpha. Alternate interior, this is beta, this is beta. So yeah, that's what I'm using. So therefore, this portion is 2 alpha. And as a result, this portion here is beta, beta. This one should be 2 beta. Well, we kind of proved that the central angle is twice the angle A, right? Angle A is alpha plus beta. The central angle is 2 alpha plus 2 beta. So where do we go from there? Yeah, so we basically do the same thing in reverse order this time. Yeah, we can do the same thing reverse order. I can connect B and D. I mean B and O, I should say. Connect this. All right. So I can, well, there's this big angle, let's call it theta. And then there's this tiny angle here you guys can barely see. Let's call it, well, gamma, I guess. So this tiny angle here is gamma. Why? Because we have obviously these 3 segments are congruent. So we have a bunch of isosceles triangles. For example, BOD is an isosceles triangle because the 2 legs of the triangle are the same. And similarly, BOC is also an isosceles triangle. So if I were to extend BO, which you guys can barely see, this angle here is 2 gamma. Oh gosh, that's okay, terrible. All right, can I just get rid of all this? All right, so that thing is 2 gamma, and the rest of it is what? That the rest of it would be, because this portion is theta, that portion is also theta, so that would be 2 theta. Right, so therefore this whole central angle is 2 gamma plus 2 theta. 2 gamma plus 2 theta. But wait a second. Earlier we established that that central angle DOC was what? Earlier we established DOC was 2 alpha plus 2 beta, right? And now we're saying it's 2 gamma plus 2 theta. So better these two be equal to each other, right? They must be congruent angles. And dividing both sides by 2, the 2's cancel, and boom. So this angle which measures gamma plus theta better be equal to alpha plus beta, and there you go. So that's one, I guess, fancy way. Here, the fact that I made use of is connecting drawing the additional lines so that I can have the center of the circle involved. And along the way, I established a new result. Apparently, the central angle subtending an arc measures double the angle on the circle, which subtends the same arc. All right, so that's pretty good. Let's have a look at the next one. How about this one? What should I do? Well, first tell me what is the statement, and then how I can proceed. Well, yeah, go ahead and let's label the angles. There is something which is a little bit misleading about the picture. What do you guys think are misleading? Yes, we need to show these two angles are congruent. That's correct. This angle, this green angle, and this blue angle. We need the blue angle is on a tangency. Do you guys see that? So there, this is a tangent line to the circle at C. Yeah, the thing which is kind of misleading is AC is not diameter, right? Not necessarily a diameter. Is not necessarily a diameter. It works for any configuration. So don't be misled by that. In fact, I might as well just redraw the picture, I guess, so that it's definitely not misleading, right? Okay, so hold on. Why is the blue angle and equal to the green angle? Yeah, that's the question. We need to prove it. Okay, let me draw a new picture because unfortunately the previous picture is kind of misleading. Sorry for that. Maybe you guys can communicate with Akopian, the author of the book. Tell him that, hey, one of the pictures is a little bit misleading. Okay, so we have this tangency. I think we labeled it as C earlier. Yes. And then we have the center. I'll be careful so that I will make sure my line doesn't go through that center. So the claim is the following. We have this triangle ABC. Then the claim is that this angle here, well, is apparently, let's call it alpha, is congruent to this angle, beta. So show alpha and beta are actually the same angle. So what should I do? Okay, so some people are suggesting I should use the central angle theorem that we just used a minute ago in the previous question. So they are saying that this angle here, holy, now this picture is misleading. This angle is not 90 degrees, okay? Holy, okay, anyhow, so this angle is 2 alpha, yes. And, but where do I go from there? Oh, we have some isosceles triangle, yes. This triangle is isosceles because this is the center of that circle. These are the radii, OB and OC are the radii. So necessarily we can easily measure these two angles. Can you tell me what those two angles measure? OBC, angle OBC measures what? Oh, wow, okay, yes. Because those three angles on triangle OBC, this angle is 2 alpha, so this angle should better be 180 minus 180 minus, well, okay, so because these two are congruent to each other, right? OBC and OCB are congruent angles for sure. Let me make note of that first. OCB. These are congruent. Then what I can do is angle OBC as a result can be written as 180 minus 2 alpha, this top angle, the all divided by 2. So which is just 90 minus alpha. All right. So yes, I know that this angle here is 90 minus alpha. All right. So what do I do next? I'm still missing something, an observation. Yes, I still didn't involve the fact that this is a tangent line. How can I involve that? What's a special property of tangent lines? If a line is tangent to a circle, what happens? How do we know it is tangent? Yes, the perpendicular at C happens to go through which point? Through the center. Ah, OC is a special segment here. This is a 90-degree angle, in fact. Ah, so that solves the problem. So basically what we did use is we used that central angle theorem and the fact that the tangency is created by that tangent line. So necessarily the sum of these two angles is 90 degrees. 90 minus alpha plus beta is 90 degrees. So the 90s cancel and boom, minus alpha plus beta is 0, which is exactly what we needed to show. Whew, okay, so that was something. Let's go to the next question. Miquel theorem. I think it's a little bit early to have that, but okay, so let's just do it anyways. So we have this triangle ABC. What is the claim here? What is the statement that we want to prove? Well, it's not me, Akopian is doing it. Check his book. Yes, so there's apparently this third circle. So first you start by drawing these two circles. One way to do it is, I guess, the following. We can first label 3 points on the circle. I mean, sorry, 3 points on the 3 sides of that triangle. So we label 3 points on the sides of our triangle. And then we first draw these two circles. I can call this one omega B, which is just the circle BDF. Usually we represent it like this. This is customary to, what should I call omega C? Which circle is this? Yes, this is EDC. Do you guys know why it is customary to use 3, like this notation to represent a circle? Like why could this be customary? Like EDC. Ah, nice. Yes, that's right. Okay, good. You guys know it. Anytime you have 3 points on a plane, any 3 points, doesn't matter, it defines uniquely, uniquely describes a circle. There's only one circle which can go through all those 3 points. Because 3 points uniquely describe a circle, we can represent, in general, we represent circles like this because they uniquely describe it. And that also explains why we can talk about the circumcircle of a given triangle ABC, the circumcircle, right? So because we are drawing a circle which goes through the 3 vertices of a triangle, so it is unique, right? So that's pretty good. All right, back to our picture. So I labeled 3 points on the 3 sides of my triangle. I did draw my first circle here, omega B, which is circumcircle of BDF. Then I did draw omega C. The claim then is, well, obviously I can draw AEF as well, omega A, which is when I draw AEF, that very last circle, apparently that last circle goes through that one of the 2 intersection points of our 2 circles, earlier circles. You guys see that? This is a very celebrated theorem, by the way. It turns out that it's, yeah, this is how, well, okay, anyhow, so I don't want to confuse anybody. But yeah, so this is where spiral similarity, yes, is established. So for those of you who play video games, I mean, my generation, we used to play video games on 2D, right? Where like, but now video games are 3-dimensional, so probably they are using some other stuff, I guess, but uh, like quaternions or something like that. I think they are using those number systems. But yeah, anyhow, so what do we do here? How do I establish that that circle contains that point of intersection between the earlier intersection of these two circles? So we might as well start with a new picture. So that, oh, wow, I'm running out of space already. Yeah? Okay, so let's go ahead and redraw that picture. So we started like this, just to remind you, ABC. Then we labeled 3 random points, doesn't matter which 3 points are. I think we labeled them as DEF, DEF. The claim is the following. First, let's intersect. Oh, shoot. Okay, so first, let's make sure that they intersect inside the circle. By the way, the theorem is still correct, even though they don't intersect inside. Even when they intersect outside, outside the circle, the statement is still correct, but I wanted to keep things inside. So yeah, let's just do it like this. Okay, DEF. Okay, let's go ahead and draw the circles. There you go. That's the first circle. That's the second circle. And now the claim, oh, wow, that's more like an egg, but pretend it's a circle. Oh, gosh. Okay, let's do it again. Yeah, it should be a little bit more. There you go. All right. The claim is that if I label this point as X here, what's the claim we want to prove? Show what? Show X is contained where? Yes, show X is contained on circle AFE. That's it. That's what we want to show. AFE, I can always draw a circle, but that circle going through X is no ordinary business. Okay, so what do I do? Okay, some of you guys have a 2-word proof. I like that one. So someone said, it is just the radical center of these 3 circles done. All right. No, that's not acceptable. But instead, we can do something better. So why don't we just go ahead and connect so far what we have? DX can be connected, FX can be connected, XE can be connected. Do you guys see in geometry, there's a lot of creativity where you need to so far all the proofs that we did, we connected some line segments, we did draw perpendiculars and things like that. And by the way, I think I mentioned it last week as well, right? So it all started with geometry, right? How do you guys know math all started with geometry? Because of the Greeks, yes, the Greeks. Yes, the Greeks had a serious concern. Well, you know, they were mostly philosophers, and they had a huge concern about understanding the universe around them, right? Understanding the universe, and then what is our role inside the universe. Okay, so this is not a philosophy class, right? And then they realized that they had to make some measurements to understand the universe, right? So that's when they started working on geometry. So it all started with geometry. Well, obviously, during the centuries, like during the 6th, 7th century, algebra was invented. Then during the 16th, 17th century, calculus was invented. And then abstract algebra, more abstraction, more. But ultimately, everything is back to this thing, right? The thing is, geometry is both a is nice and not nice. It's nice in the following sense. It's nice in up to 3 dimensions, where your intuition can help you. Like, it's nice to see those visual drawings, but it's also a curse. After a while, your intuition will just take you up to a certain point. So how are you going to imagine a 4-dimensional shape, right? Yes, or a 5th dimension. That's when algebra comes into the picture, right? And other areas in math, they come into the picture to reinforce our commitment to understand the universe, the geometry, basically. But geometry is actually the center of the whole action, actually, in the end, right? Anyhow, so I think the whole idea here is to chase angles, right? Did you guys started chasing angles? For instance, can you tell me what this angle here measures? Angle FXD. Let's go ahead and chase those angles. Angle FXD measures. Yeah, this is not a special triangle. So yes, it is 180 degrees minus angle B. Do you guys see why? Because obviously X is in the intersection of these two blue circles. That's how we defined x as one of the intersection points of these two circles. So because this angle here is a b and bfxd is cyclic, so this one is 180 minus b. But by the same token, I can easily establish, okay, let's move that x over here. I can easily establish that this angle here, angle dxe, how about that? dxe by the same token, that thing is equal to, yes, if this angle here is a c, well, that one better be 180 minus c. Aha! But then it is natural to next calculate which angle. So this one is 180 minus c. What is the next angle that I would be extremely interested in calculating, measuring? Yes, it makes sense to complete the circle with the angle here. Yeah, it would be interesting to see what fxe would measure, but it would just measure 360 degrees minus 180 minus b minus 180 minus c, right? That's it. And if you do so, what do you get? What measurement comes out of it? So 360 minus 180 minus b minus 180 minus c. Yes. If you subtract them, so 360s and the 180s cancel, we are left with b plus c. Now, think about this quadrilateral A, F, X, E. These two opposite angles, they add up to, well, in order for us to show that those two, like this quadrilateral is cyclic, we need to establish that these two opposite angles add up to 180, which they are, right? This is angle A, this is B plus C, but look at that. A, B, C is just a triangle. Of course, the sum of its internal angles would be 180. I'm done. So therefore, this quadrilateral here is cyclic. Here along the way, I made use of one result that I think I didn't mention it to you earlier. So let me just, how do you show 4 points are concyclic? 1, 2, 3, 4. There are two methods. Either you establish this angle and this angle, they are congruent. If those two angles are congruent, then necessarily those 4 points are cyclic. So therefore, the earlier result that we proved was an if and only if statement. Remember earlier we started with 4 points on the circle, and then we established those angles are congruent. If the angles are congruent, then the points are concyclic. So this is one way to establish those 4 points are concyclic. Alternatively, if you have 4 points again, all you check is the opposite pair of angles, any opposite, either these two. So if you can show that alpha plus beta is equal to 180, again, that establishes that those 4 points are indeed cyclic. All right, so this is something that we used in this proof here. Yes, converse of Ptolemy, if we know the side lengths. Converse of Ptolemy. Okay. Maybe. Okay, so this was a good proof. How about this one? I need a statement. Yeah, what is the dot in the middle? Someone is asking, do you guys can guess what is the dot in the middle? Yes, it seems that's the center of this circle, which is the circumcircle of our triangle ABC, right? So what is the claim of the problem? I mean, the claim of this picture. What is that picture trying to communicate to us? Yes, it is trying to communicate to us that this green angle is congruent to this blue angle. Oops, I thought I did click on the blue. Yes, that blue angle, why would they be congruent? Equal angles. Yes. All right, so, but it's kind of curious, right? So this segment here is the segment which connects O, the circumcenter, to one of the vertices. This one is the altitude drawn from vertex A, right, to the opposite side. All right, Well, obviously, yeah, like you guys are suggesting, there are thousands of ways to prove these results. No single way. Awesome. So someone is suggesting we can draw an angle bisector. Okay. So I'm assuming you are mentioning the A angle bisector. And then what do I do with it? Okay, so I did draw an angle bisector. Actually, now that you said it, I think this works. I was planning to prove it in a different way, but this proof is better. Thank you for doing that. Okay, wow, I wasn't expecting that. So what is special about this point? So suppose that this new red line that I just draw, so let's label this point as So what is that the significance of this point M? If that AM is an angle bisector, AM angle bisector. Angle bisector. Yes, because it's an angle bisector, it will bisect the chord BC into two equal portions. So M is the midpoint of that chord. That's right. So again, we started with this angle bisector here. So this is an angle bisector. Let's make 3, 1, 2, 3. All right, there you go. So it's an angle bisector, and necessarily BM is equal to MC. BM, arc BM, measures the same as arc MC. What's next? So M is the midpoint. Ah, nice. Okay, so Henry is asking me to draw, wait, I think it's Henry, yes. He's asking me to draw OM. So what is the significance of OM? What good can come out of OM? Yes, that's true. OM and OA, they are both radii, so they measure the same length. So let me just put some mark next to it, R and R. So then what? Yes, it's an isosceles triangle. So if I measure this one as alpha, this one is also alpha. Okay. In fact, I think it's, well, okay. Ah, okay. But yeah, so yeah, I think Henry has another idea here. He's suggesting that OM has another special purpose. What other good can he do as it relates to BC? What can you say about OM and BC? Yes, do you guys see that? It's a perpendicular bisector of BC. Do you guys see that? Well, this is another thing that maybe we might have had to prove it, but let's assume that you guys already know it. On any given circle, if you draw a chord and if you use a perpendicular bisector, the perpendicular bisector will go through the center of our circle. And because M is the midpoint, if I connect OM, then it will necessarily be perpendicular to BC. And so these two segments, they are also congruent. Right, so this is a midpoint in a sense on that segment. Does isogonal conjugation work? Of course, that's the whole point of this thing. This is a special thing. Yes. Yes, now we are in a very special position because look at that. OM is perpendicular to BC, AH is perpendicular to BC. So as a result, what happens? OM perpendicular to BC, AH perpendicular to BC. Let's write that down. OM perpendicular to BC, but AH is also perpendicular to BC. Aha. So that implies, well, these two imply that, well, OM is parallel to AH. But if OM and AH are parallel, there's an other angle which measures alpha due to alternate interior angles. Which other angle also measures alpha? Nah. Most people says, nah. Okay, good. This is also alpha. Do you guys see? Because these two lines are parallel. Of course, we have a transversal AM, and it creates two alternate interior angles. But now suddenly, look at that. These two angles are both alpha. Earlier, we started we did draw this additional line AM, such that AM was such that it split the angle BAC into two equal portions. So this portion is equal to that. But those tiny portions are both alpha, so necessarily the remaining pieces better be equal to each other. You guys see that? And as a result, we are done. Okay, so that was fast. And yeah, like I said, this wasn't my intention. Yeah, I was planning to solve it in a different way. If you guys want, let me show you an alternative way to solve it, which is pretty good. So this solution is good. Actually, the more I think about it, maybe my solution doesn't even exist. Actually, let's see if that would work. Okay, so again, we have triangle ABC. We drop a perpendicular. And then we also have the center. Connect the center. One thing I was thinking about is, oh wow, parallelogram, AHMO. AHMO is a parallelogram? Wait. Oh, H is the, you mean orthocenter H. Oh, okay, okay. Yeah, maybe. Okay, in fact, what I was thinking is the following. I was thinking of connecting BO. So can you guys tell me what is the measurement of this angle here at the center? Angle AOB. AOB measures what? Yeah, it's a central angle. Look at the arc that it subtends. So that arc is also subtended by this angle. Yes, this angle was C. So therefore, this angle here is 2C. So one idea is not to just draw one perpendicular line. Can you tell me which perpendicular line? Let me give you a hint. Because we already know that this angle here measures what? This measures, can you tell me what that one measures before we do further, we go further? There's a right triangle. AHC is a right triangle. Yes, that's 90 minus C. So then necessarily, so I need to prove that this angle is also 90 minus C. So how can this be done? Which perpendicular can I draw? Yeah, I'll scroll to the previous way in just at the end. So yes. Okay, so someone suggested to draw a perpendicular to one of the segments from O. Yes, why don't we just draw a perpendicular from O to AB? If I draw a perpendicular from O to AB, what good can come out of it? Let me label this point as N. So yes, AOB is no ordinary triangle, right? It's a special triangle. It's an isosceles triangle because two of its side lengths are both measuring R, the radius of our circle, because O is the center. So because it's an isosceles triangle, an altitude on an isosceles triangle will split the base into two halves, and also it will split the top angle C and C. Suddenly this angle happens to be 90 minus C, right? Because you have A and O is a right triangle where this angle is C, that angle is a 90, so therefore this angle better be 90 minus C. I don't need to do that. Okay, why? I could have done it much faster. How? LSOS, what does that mean? No altitude, base angles theorem. Okay, yeah, well, apparently there's other ways to do it. Yes. Okay, base angles. What do you mean? What's that theorem? Because it's isosceles. Yeah, so probably. Awesome. So, okay, so, oh, someone mentioned they wanted to see, oh, AOB is 2C here, 2 angle C. Someone mentioned they wanted to see the first picture, so there you go. Okay, so there's a couple of interesting questions. One of the questions, okay, so I'm assuming you guys already did draw the picture. Okay, one of the interesting questions is, how do you come up with drawing these lines? Like, how do you know which lines to draw? Yes, so you build your skills. It's like yeah, so it's not intuition for sure, it's practice. So if you are interested in these topics, there's a great book that I can highly recommend. It's called Challenging Problems in Geometry. It's an old book, but it's a really good book. right? So it's a good book by Posamentier. Posamentier. I think if you search it on Google, you should be able to find the book, or you can purchase it. I have 2 copies of that book in my house. So can you imagine? Like, I really enjoy this book a lot. So the book starts very smoothly with angle chasing and circles, and then over time it gets really interesting. All right, so here comes our next drawing. Yeah, so exactly. So what is the statement here? Okay, let me give you a couple of minutes to think about this one. Or, well, when I say minutes, maybe just 1 or 2 minutes. We saw this before in another context. Do you guys see when we saw this picture before? It was for another purpose. I don't remember if we did it here or in the Thursday class. Do you guys remember the version that we saw? Okay, so let me draw another picture while you guys are thinking. If you guys want, you can have a screenshot, or can you please first draw it on your paper, and then I'll show you another configuration. Let's first solve that other configuration. 2 types of cyclic quads with centers. Yes, kind of. Yeah. Okay. All right. So yes, the dashed line is an altitude. So the claim of this theorem is the following. If you draw the altitude here, and then, well, okay, so here you go. You start with a triangle. Let me first mention what this result is asking us to prove. So ABC here, AH is an altitude on that triangle ABC. And then we mark 2 points here, D and E. We draw the circumcircle of BCED. So BCED is circular. Then when we further draw ADE, it turns out, incidentally, the center of that circle happens to be on the altitude of that big triangle. Yes, AH contains the center of ADE. Okay, there's a special case to this thing. So let's have a look at the special case first. The case where D and E are special points. They are, what points am I thinking about? Let's first prove that, and then let's prove this one. Where D and E are actually the foot of the altitudes from B and C, right? Do you guys remember that? Yes, the feet of the altitude. So, okay, so let's go ahead and draw this picture again. I'm going to change the statement. This is a special case of the previous problem, basically. All I do is draw the 3 altitudes from B, A, B, C. Oops, maybe it's this side. Okay, there we go. So then, well, obviously these 4 points are definitely constant. Well, first let me label these as D, E, F. Do you guys see why this is cyclic? Yeah, because of those 90-degree angles here and here. Remember earlier we suggested that if those 2 angles are equal, then this is a circle, right? So that's exact. In our case, these are 90 degrees, so it's even better for us. That tells us that BC is actually no ordinary chord, it's a diameter, yes. So this is a diameter BC. Okay, so then we can obviously now draw the circumcircle of AFE. And now our goal is to show that AFE has the center on AD. Why is it that AFE, the center of that circle, is on AD? Well, first of all, let's just put things in order. There's something weird about that green circle. Can you help me draw it? I had some doubts while I was drawing it. I wasn't sure if that circle will go through that orthocenter H. Would it? What do you think? Would it pass through the orthocenter? If yes, explain why. Yeah, saying just yes is not enough, right? Yes. Okay, good. Yeah, exactly. So first of all, first let's establish that H is on this circle, namely AFHE is cyclic. Well, obviously this is a 90-degree angle. This is also a 90-degree angle. We have 4 points, AFHE, such that the opposite angles add up to 180 degrees. They are supplementary angles. So necessarily H has got to be on that circle. You guys see that? But moreover, it gives us something else for free, and it is that because these are 90-degree angles, the diameter of that green circle happens to be on AH. In fact, it's the midpoint of AH. Yes, so the midpoint, call it M, for instance. Do you guys agree? So this is a special case of this one now, this one, which is also, even though D and E are not the feet of the altitudes here, we put this additional restriction that E and F are the feet of the altitudes, even when they are not, as long as there is such a circle here where E and F are on that circle, which they are here, then even then, this point has to be, so the center of our circle has to be on AH. All right, so let me just remove that center. So let me try to draw the altitude like, okay, so I totally disappeared the center. So we don't know if the center is on that red line. So that's what we want to prove. What should I make use of? What can I use? Aha, a center. Yes. The center of what? Draw BE and, okay, so there's a couple of ideas. BCEAD, BCEAU. So earlier we proved something very interesting. What was that result? Do you guys remember that? What did we prove earlier? Just one question before, I think. Something, yes. What was that something? Let's remember that. Remember what we proved. Okay, so this statement, what was the statement? I mean, after the proof, it seems it totally disappeared, but the statement was that angle CAH and angle BAO, they are congruent. So basically what it is telling you is that, okay, let me just do it here again. So whenever you, actually, let's first draw a circle. So if you have a triangle, oh gosh, okay, and this is the center of that, circumcenter of that triangle ABC, then the claim is that the angle here, angle BAO, and if I were to drop a perpendicular here, and this angle, they are congruent angles. Okay, that's interesting. All right, so don't forget about this. So this is an important thing that we already proved in 2 different ways, and some people suggested we could have done a lot of other stuff. All right, so now back to this picture. Okay, yeah. Well, if anything, I already know the measurement of this angle. Well, it's obviously 90 minus C, right? And if I were to draw another angle here with that same measurement, 90 minus C, I know for sure that it would have met with the circumcenter. I mean, sorry, it would have met with this, yes, the center of the circumcircle. Okay, so something like that. So that new green circle, it has center somewhere here. I know that for free, right? So this angle here is 90 minus C. All right, so far, that's the only connection I can see between this question and the previous question, but I had to come up with a third new circle, which is kind of annoying. Did we had to do it? First, do you guys agree that it might be a good idea to just connect some segments here? So for instance, I can connect DE. There you go. And then suddenly life is totally different. There are some similar triangles in this picture. Do you guys see that? A ton. For instance, triangle ABC is similar to another triangle. Which one? ABC, not ADE. Yes, AED. Aha. Now check this out. Why would that be? Because this angle here is a B. Well, this angle is also a B. Do you guys see why? Because of that cyclic quadrilateral BDEC. Opposite angles, they are supplementary angles. So this angle is 180 minus B. So as a result, the supplementary angle is B. But by the same token, this angle here is a C. Oh gosh, so I'm not sure if I will be, okay, so this tiny angle here, okay, let me draw it. So this is a C. So what happens here? Oh, what is the question? The question is, okay, let me remind them. So some people are asking what is the question again. The question is this. Let me quickly draw the question here one more time. So the question is this. Start with a triangle, any triangle, ABC. Just pick any, just draw any circle you want. Let's say like that, in such a way that it hits the two sides at the points D and E. Then the claim is the following. If you draw this circle, ADE, let's go ahead and do that. The claim is that, well, my picture sucks, obviously. So the claim is that the center of this circle happens to be on the altitude. All right, so the altitude of the original triangle. So the center of this green circle apparently is on the altitude. Unfortunately, my picture is not very good. So, but that's the claim. Center of ADE on AH. If you label this point as an H, is on AH. That's what we want to prove. Okay, so back to here. So far we had a couple of observations, but we still don't know. So far we established that we have a similar triangle here. I mean, a pair of similar triangles, but the orientation of these two triangles are, they are reversed. They have the reverse orientation. What does that mean? So technically, if you have two triangles like this, okay, let me give you another observation. So for instance, if I have a triangle ABC here, ABC, and if there's another triangle, say for instance, DAE, that's one way we can have a similar triangle, right? These two sides are parallel, and triangle ABC is similar to triangle ADE. That's one way they can be similar. Or alternatively, and that's what we have in our question, so our ADE is not like that. Our ADE is tilted. Do you guys see that? Our ADE is such that it's like that, oppositely similar, like these are two angles, so DE here. So the similarity is still ABC, ADE, but in our case, and then this one is double here. Do you guys see that? So it's kind of, it is as if you want to align them again, what can be done? What type of geometric transformation can I do so that ED would be parallel to BC and I would still remain inside triangle ABC? A translation won't do it. Yes, a reflection will do it, but how? Reflect across what? Yes, if I were to reflect now, believe it or not, so let me just draw another pick color, so a blue line. So this is an angle bisector. If I were to reflect ED across this angle bisector here, so this is an angle bisector, then ED will turn into this. Check this out. It would go, because it's a reflection, this is a mirror, right? So this is my mirror. So ED suddenly becomes, so this D will go here, you can call it D prime if you want. The E will go here, E prime, but now they are correctly aligned. Do you guys see? The similarity now works perfectly. Like you have the parallel line, something that you guys are familiar with. So there are two ways you can construct similar triangles here. So this is something that you should be worried sometimes in terms of configurations. But now going back to, wait, what happened to my picture? Oh, there you go. So going back to my original picture, now how can we wrap up the whole story? I think we have all the ingredients that we need. All we need is now to just combine these ingredients and boom. Like we are just circling around the answer, I think. Okay, so Brian says, draw the angle bisector. Done. Reflect. Done. Oops. Oops, hold on. Once you, oh gosh, my pencil is stuck. All right, sorry for that. Okay, there you go. So we end up with our parallel thing, right? After we reflected, so E goes here, D goes here, D prime goes here. But then interesting, okay, so think about now, instead of, forget about triangle ADE for a minute. Instead, let's focus on triangle AD prime E prime. Where is the center of that, the circumcircle of AD prime E prime? Where is the circumcenter of that triangle? AD prime E prime. Well, clearly AD prime E prime, D prime E prime is now parallel to BC, right? Do you guys agree? For the reason that we just explained a minute ago, huh? So those two are parallel segments. BC is parallel to D prime E prime. But now the good news is, in terms of orientation, they are also aligned. Now the two triangles, they are properly oriented, right? So because of those parallel segments. So necessarily, I think everybody would agree that the center of AD prime E prime is on which segment? Where is the center of AD prime E prime? The circumcenter of AD prime E prime. I don't even want to draw the circle itself. But if I, okay, let me just, I can't resist it. Okay, it's such a beautiful construction that I really, well, maybe I'm sure right now overkilling the problem, but it's still, well, something worthwhile. So what's special about that circle, AD prime E prime? Do you guys see that it is tangent to the green circle over here? Why is the red and the green circle tangent to each other? Yes, because yes, ABC is similar to E prime. Huh? Wait, what did I call it? Yeah, AE prime D prime, right? AE prime D prime. And because they are also properly oriented with that parallel line, D prime E prime is parallel to BC, everything will be corresponding with each other. So the circumcircle of AE prime D prime and ABC will be tangent at A because there's a center of homotety at A. There's a homotety taking that little triangle AE prime D prime to ABC. You guys see that? It's more than they are similar. They are similar embedded inside the same picture. As a result, whatever is the circumcenter O prime here of that little red circle, it will be dilated to O. And do you guys see that? We don't know what is the ratio of dilation, but still, the homotety. Homotety means, okay, let me just show it here. So you have a center of homotety, H, well, okay, let's call it T, for instance. So what it does is, for instance, if you start with any shape here, let's say you start with a triangle here, like that, then you can dilate it. All you do is each of these points A, B, C goes to these new points, A prime, B prime, C prime. So A prime, B prime, C prime is similar to ABC, and all the angles are preserved, right? So these angles are preserved, this one is preserved with this one, and so on. Awesome. But yeah, so because now O prime is here, aha! So now I know, wait a second, if the circumcenter of AD prime E prime is on OA, which is this prime, this point O prime, now how can I finish the question then? Now I can reflect it back to the original, right? The original circle, remember that this red circle and this black circle are just reflections of each other. Why? Because D is a reflection of D. So D prime is a reflection of D, E prime is a reflection of E. So the circumcircle of ADE and the circumcircle of AD prime E prime, they are just congruent circles. You guys see that? Yes, just reflect back that red circle into the black one, and then boom. So necessarily, the center has to be on the altitude simply because of the property that we mentioned earlier, that these angles, they are equal only when, so if this line goes through the circumcenter and this one is on the altitude. Okay, so yeah, this was probably a little bit kind of advanced, but it is still good that you guys can use reflections and so on. Yes, reflecting it back, it proves, it finishes the proof. It tells us necessarily that because of the earlier result that we proved, because those two green angles over here and here, because they are equal, then when I reflect it back, the center, which was on OA, now will end up being on HA for that black circle. So the circle, the red circle, its center is on OA. The black circle, its center is on AH. All right. Good. So, okay, so this one was slightly advanced, like we said. Actually, one more thing about this picture. Remember how earlier, the same thing happens here, right? So triangle ABC is similar to triangle AEF. Here, whenever you have a, like, because this is a special case with a right triangle, more than that, we also know the dilation ratio. What was it? Do you guys remember? What was the ratio? If 1 to what? So those, well, after you reflect across the angle bisector, what is the ratio of similarity between these two triangles? Do you guys remember that? No, wait, no, not 1 to 2. 1 to, let's see if anybody remembers it. I thought we did it earlier. Maybe yeah, maybe it was in another class. Yes, it turns out to be, okay, I can't resist. Okay, so it's just cosine A. Yeah, that's it. Yeah, if you've never seen this before, so this is a very good exercise as well. Let me actually, I can't resist because we already did so much about this configuration. We might as well just prove this result as well. So all you do is, if you check this E and F, if you connect them, like we said, this angle is a B, this angle is a C, right? But more than that, there's a 90-degree angle here. So I want to measure AF. AF, hey, I can just use this angle here. This angle is just what? 90 minus A. Do you guys agree? Cosine of angle A. Yeah, it's just a number. Whatever is the angle, so this is a general result. So as a result, if I apply sine of 90 minus A, so sine of 90 minus A, angle A, on that right triangle AFC, that is just AF to AC. Wait a second. Sine of 90 minus A is the same thing as what? Sine of, yes, that's just cosine of A equals, AF is what? AF is exactly what we needed to calculate. And then AC. AC, I can just replace it with the lowercase letter b. So suddenly AF is just b cosine A. So this length here is just b cosine of A. In a similar way, you can just use this right triangle ABE to establish that this segment here is C cosine of A. And similarly, this one would end up being A cosine of A. Wow, the side lengths of this triangle are ABC. The side lengths of this tiny triangle are A cosine A, B cosine A, C cosine A. So as a result, the ratio of similarity between them must be, can you scroll up a little? You mean the original question? Yes, okay, so I think everybody's, yeah, happy with that. Going back to the original question, if you want to take a screenshot, so this will be available on YouTube probably by tomorrow. So you can check our YouTube channel. Some people was asking what is the channel address. It's just, if you search Momentum Learning on YouTube, you should be able to find those free lectures. All right, so barycentric coordinates, no way. I'm not gonna use mass points. All right, I'm just gonna go ahead and skip some of the questions so you guys can easily do some angle chasing here. Yeah, so I'll just leave it to you as an exercise. What is the claim here? The claim is that if you have a quadrilateral ABCD and you have angle bisectors here, A alpha alpha, beta beta, gamma gamma, and theta theta, or delta, let's call it delta, delta delta, then what is the claim? If you extend pairs of angle bisectors, these two, they meet here, these two, they meet here, and then which two? Oh, this one and this one, they meet here. That one and that one, they meet here. So those are the 4 meeting points of pairs of either, like all the adjacent ones, right? We have 4 adjacent pairs. So when they meet, then what is the claim? Oh, sorry. Some people, they had problems with the previous question. All right. Yeah, check the video like on YouTube. So you will see, I think I explained the reasoning twice, but yeah, it was a little bit of an advanced problem, the previous question. So let me not go back to that one. All right, so yes, we need to, the claim is that these 4 points are cyclic. I think it is straightforward angle chasing. Just figure out what is this angle using these two in terms of delta and gamma. Write out this one in terms of alpha and beta or whatever you want. And I show that these two angles, they add up to 180 degrees. I think it's straightforward. All right, so here's another one. Okay, again, you guys just, the claim is obvious. Start with a chord AB on a circle. This is the midpoint of the chord AB. Then from that midpoint, draw two new chords, D and E. So MD and ME. Then the claim is that MD and ME, they intersect AB at K and L, show that DKLE is cyclic. All right, so show DKLE concyclic points. These are all standard angle chasing problems. All right, so like I said, so you guys, there's an abundance of books about this. So this one is our familiar theorem. Which theorem is this? Yes, angle bisector theorem. How in the world do we even prove the angle bisector theorem, right? Yeah, so I'll just leave this one also as an exercise for you guys. So the angle bisector theorem, if you've never seen the proof, it's worthwhile looking at it as well. Yes, you have to come up with a new line. You have to draw some parallel lines. You can't just, yeah, you can't just, angle chasing won't be sufficient here. So you have to draw some parallel lines and establish some similarity or something like that. Go back to 1.13, here you go. That's the statement. Show that DKLE is concyclic. So we started with an arc AB. M is the midpoint of that arc. MD and ME, we draw it. We let it intersect chord AB at K and L. Show that DKLE better be cyclic. Yeah. This one actually looks projective as well. All right. So next one. This one also has a special name, I think. Yes, Pitot's theorem. I don't know, or Pitot's theorem. This one is actually extremely simple to prove. So we might as well prove it together. So what is the key idea of the proof here? Okay, so label this. I did it. And then label the tangencies. I don't know, DEF, DEF, G. And now, yes, the goal is to prove this statement, that opposite sides, they add up to, they are equal to each other if you can inscribe a circle inside the quadrilateral. If your quadrilateral is inscribable, if you have an inscribable quadrilateral, then opposite edges of that quadrilateral, they are equal, their sum is equal. Yes, okay, so people already suggested that using equal tangents, this segment is congruent to this segment, this one is congruent to this. When I say this, I mean BD is equal to BE, CE is equal to CF, and then DF is equal to DG. But now we are done. Why? Because if you look at this segment here, it has the total of this one, AB plus CD, right? So these two, AB plus CD. Well, it consists of a 1, a 2, a wiggle, like a wave, and a circle. And then when you look at the other side, it is the same thing. This one also has a single, a double, a wiggle, and a circle. Done. So this establishes that AB plus CD, or whatever you call it. What is this? A wave, wiggle. Where did I come up with that word? Okay, so yeah, a wave here. A tilde sign, yes. All right, so AB plus CD. So this is an inscribable quadrilateral. This is different than a circumscribable quadrilateral. In a circumscribable quadrilateral, it's a cyclic quadrilateral, you have this. What was the name of the theorem that we use for these type of things in relating to length? Someone mentioned it earlier. Yes, we use Ptolemy. This is an extremely convenient theorem. So ABCD, here AB times CD plus AD times BC is equal to the product of the diagonals. There you go. This is a different. So this one is circumscribed circle. This one is an inscribed circle. We inscribe it inside the quadrilateral. All right. So, well, this one is slightly, pretty much the same ideas. So you have this in circle of triangle ABC, and this would be the X circle, in circle. Usually we call this the AX circle simply because what? Why do we put an adjective in front of it? Why don't we just call it the X circle like we call it here? Here we call it the in circle. Why don't we simply call it the X circle, but rather we prefer to call it the AX circle? Ah, yes, because there are two more of these. Yes, there's another one on this side. Well, because we don't have enough room. Well, there's another one on that side like that. And then there's another one on this side. Yes. So it doesn't matter. The result still holds for all three of them. The claim is the following. So if you call this point as D, this one as E, the claim is that CD is equal to BE. So this is the touch point of the X circle. E is the touch point of the X circle with the side BC. D is the touch point of the in circle with the side BC. And the claim is BE is equal to CD. Can you imagine what the proof will end up using? So we need to establish some lengths. Yes. Yeah. So we need to, because there's so many tangencies, there's a tangency point here, a tangency here, we will use the equal tangents. Yeah, that's it. Just use the equal tangent. For instance, just as an example, AK, sorry, this one is K, this one is L. Yes, AK is equal to what in this picture? Yeah. Yes, AK better be equal to AL, yes. Because of equal tangents from the point A, we did draw two tangents to the AX circle, and they meet the circle at K and L, they are tangencies there. So necessarily AK is equal to AL. In a similar way, for instance, if you call this one as, well, anyhow, so you guys know the drill from here, right? And then you try to keep manipulating the length. I think, for instance, can you tell me BK, it's equal to what? Yes, BK is equal to BE. And let me also give two more labels, X and Y here. How about BX? BX is equal to what? Yes, that's right. BX is BD. And let's do two more. CE is equal to what? CE. I don't need this. Yes, CE is equal to CL. And lastly, CY is equal to, yes, CY is equal to CD. That's it. I think this should be enough to prove the desired result. So using these, mix them, and then cook the food. Obviously, cooking the food is a non-trivial task. If someone tells you, you ask your mom, hey mom, what did you put inside the food? And she will tell you whatever she put. Do you think you can cook the same food? Or your dad, as horrible as a cook as he is, if he cooks some food tonight, which you would know for sure, hey mom, did dad cook that food? How do you know, honey? Well, you know. All right. Oh, wow. So some people, their dads cook better. Okay, good. So do you think if your dad just told you what are the ingredients, can you cook the same food? Probably not, right? So because you need to know the sequence with which he puts the ingredients into the pan, and then how much fire to put it in, and then how much love to put, right? So a lot of love and so on. So the same thing here. Obviously, one way we should reorder these things. Ultimately, it should give that, but it requires some creativity, right? So you need to like practice this. If you've never cooked in your whole life, I mean, yeah, so there's no way you can. Yeah, so yeah. like cook some good food. So similarly, so you need to like start thinking about the ingredients, and yeah, so starting, and especially benefit from the people around you who know the material and so on. All right, good. So next question. I mean, this is just a fun question. I've never seen this thing in practice being used. So I'll just leave it in on the screen for just a few seconds. So if you want to, so the claim is that on this star shape, alpha plus beta plus epsilon plus delta plus gamma, they add up to 180 degrees. In fact, the proof is very simple. Yes, it has to do with just this fact that the exterior angle is equal to the sum of two interior angles, A and B here, so A plus B here. All you use is this fact. You just use it twice and you should be able to get the result. We can't use circles because we don't know if this shape is cyclic. 5 points are not necessarily cyclic, right? 3 points are always cyclic, but 4 points being cyclic is a miracle. Well, obviously in the problems they are always cyclic, but for some reason you have to show some reasoning for that. All right, so this is another one. What was the name of this result? Yes. This is called, yes, this is the power of a point theorem. Any point on the plane of a circle satisfies this relationship. AE times EB is equal to CE times ED. In fact, this thing is unique. Huh? So this is the power of the point E with respect to that circle omega. All right, so, and the proof comes directly from which result? Yes, okay, so some of you guys already seen the proof, I think. Yes, we use similarity of triangles to prove it. So if you say, hey, there's no triangle in the picture, there you go. Now you have some triangles. There's already 2 triangles. Now you have a lot of them. You have at least 6 triangles here. Actually, 8 triangles. So you just figure out which ones are similar and then try to set up the length relationships. Awesome. Actually, to be honest, I've never seen this configuration before. So apparently, if you start with 4, a cyclic quadrilateral here, then you just extend opposite sides, they meet here, and then you extend the other 2, they meet here. And then if you were to draw angle bisectors here, so this is an angle bisector, and this is an angle bisector for this one, they meet at a 90-degree angle. That's the claim. Show this is a 90-degree angle. Show, yeah, whatever. So this angle is 90 degrees, 90 degrees. So that's interesting, right? Extend opposite sides. Okay, so there are a couple of ideas. Yes, let's keep moving so you guys can work on these, right? This is because of similar triangles again. Yes, oh yeah, that's right. That tiny triangle is similar to that big triangle, and then this tiny triangle is similar, and then maybe you guys can use some, I don't know, maybe, well, is it angle bisector theorem or something? Somehow we need to make use of the fact that these are angle bisector, or maybe just angle chasing. Yeah, all right, so that's good. Next, okay, so next is triangle centers. I just have a few minutes left just to remind you of a couple of very well-known triangle centers. So what is this picture? Which center is this? What's the name of M here? What do we call it? Yes, that's the centroid. Why is it that the 3 medians, so this is, let's call it A1, oh, sorry, B1 and C1. So this is ABC. So why is it that AA1, BB1, CC1, they concur at the same point? Why would they concur? Why not like that? So like that, this is a median, that's a median, and then this is a median. Why do they have to concur? Why don't they just have, so usually 3 lines, they meet in 3 points. Why? It's really magical that they meet at the same point, right? Yes. Okay, so those who have seen Ceva theorem, the proof with Ceva is just 1 line, right? Ceva theorem. If you guys remember Ceva's theorem, we can use the converse of Ceva's theorem. So all we do is check this ratio, AC1 to C1b times BA1 to A1C times let's put it here, C1, CB1 to B1A. If we can show that this is equal to 1, then we are done. Is this equal to 1? When is this over? In 4 minutes or maybe 5? Yes, this is equal to 1 because AC1 is equal to C1b. The second one is also equal to 1. This ratio is also equal to 1. And finally, this one is also equal, all of them equal to 1 because in each case, these are midpoints, right? So 1 times 1 times 1, by the converse of Ceva theorem, these three Cevians, they meet at that point. Well, these three medians, I should say, they meet at the centroid. Yay! They cancel out and there's a 1 left. Okay, how about this one? Yes, why such a point exists? Why do we have an orthocenter after all? Wouldn't it be nice if there was no orthocenter and so there was no question about it? Why such a thing called orthocenter even exists? Yeah, so yeah, all you do is you draw three perpendiculars and somehow miraculously those three perpendiculars, they meet at the orthocenter. Yeah, so for this one, I think we need a little bit more, yeah, machinery. Just Ceva by itself, I don't think will work. So you need to also mix it with trigonometry. So Ceva plus trigonometry. All right, but the key idea is the same thing: A1, A2, A3. So Ceva has also another version, right? Trigonometric Ceva, trig Ceva. In the case of trig Ceva, instead of comparing the ratio of this to this, you just compare the sine of this to the sine of this angle. But then suddenly this is extremely useful. Why? Because we already know the measurement of these angles. For instance, what does this angle measure? Yes, that's 90 minus C. And similarly, this one is 90 minus B. Do you guys see why? Because you have this right triangle here. And in that right triangle, we already have angle C here. So therefore, this one must be 90 minus C. So, and you pretty much do the same thing here. This is 90 minus A. This one is 90 minus C, and so on. This portion, when you extend this portion here is 90 minus B. This portion here is 90 minus A. Now you can use something called trig Ceva, which basically tells you that the ratio, like I said earlier, the ratio of the sines. Okay, let's check. For instance, let me start from this orientation. This to this. Sine 90 minus C to sine 90 minus B times sine this, sine 90 minus A divided by sine 90 minus C, oops, 90 minus C times, and then this one to this one. Sine of 90 minus B to sine of 90. If I can show this is equal to 1, then I'm done. But wait, this is perfectly symmetric. This cancels out with that one, this one with that one. This, yes, it's 1. Done. So then maybe some of you guys might wonder, hey, let me have a look, let me revisit Ceva. Where does it even comes from? So Ceva is an amazing theorem which explains to you under what conditions Cevians they meet at a certain at a single point. This is Ceva. Whenever you want to show three segments, they are concurrent, you use Ceva. When you want to show 3 points are collinear, you use what? Yes, that's Menelaus. Because it's magic, right? So 2 points are collinear by definition, right? So 2 points define a line segment or a line. But 3 points, it's hard to have 3 points collinear, and Menelaus' theorem tells you the conditions for which this can happen. All right, wow, okay, so wow, I had so many other configurations, right? So obviously the angle bisectors, they meet at the center. Again, you can use trig Ceva here. They meet at the in-center, and the angle bisectors, that's pretty cool. And yes, in the previous question, trig Ceva, we could have turned it into a cosine. The sines, yes. Here, this one, the Gergon point, it's amazing, right? So compare the two pictures. They are different pictures. Do you guys see that? Here, the angle bisector does not necessarily meet the side at the touch point. Oh, let's extend it here. It meets at another point than the touch point. The touch point is where the 90-degree angle happens. So these are the touch points of the in circle, and apparently when you meet them, again, they meet on the circle. The proof of this one is actually straightforward with Ceva. Do you know why? The corresponding point is very yeah, this is our last problem. Okay, so do you guys remember? So let me call these ABC. Let's call these points DEF. Can someone tell me the measurements of AF? Does anyone remember how to calculate AF? Yeah, it's equal tangents, yes. This one is S minus A. Do you guys remember this, where S is the semi-perimeter? BF is S minus B, and this one is S minus C. Do you guys remember this? Yes, where S is the same perimeter. Yes. So therefore, if we just use Ceva, let's check if Ceva, the converse of Ceva, works. So we need to show that AF to FB times BD to DC times CE to EA is equal to 1. Let's see if that's true. AF is just S minus A to S minus B times S minus B to S minus C times S minus C to S. Hey, the same thing. S minus A is cancelled, S minus B is S minus C is cancelled. That's 1, and we are done, right? Awesome. So that's it.